very much, Todd. Thanks everyone for being here. And so yeah, I'm gonna just kind of give a an overview of all the stuff going on with the Southern African Large Telescope. There's a few of us here from the observatory, and Carol and Brian will be giving a talk tomorrow about some more work at the observatory. And but yeah, feel free to come up and ask us about what's going on at the observatory. It's a great place to work and a lot of fun challenges to face. And so here are some of the challenges that we are facing. But we do use Python a lot, especially with the SALT and with the data coming from SALT. And so, I mean, we basically do use it as a scripting language, like a lot of other people do, to actually kind of glue things together, and particularly for running our pipeline. Our pipeline is very important for actually allowing an interface for the astronomers, so building graphical interfaces with the astronomers to allow them to look at the data, analyze the data, but also for monitoring our performance of the telescope. And so building things which actually produce and record the outputs and the results. And obviously very important for us for doing the data reductions, for getting rid of systematic errors in the data, for getting rid of, for calibrating the data. This is really what we actually mainly use. This is really the heart of what we do, especially for our investigators who are all around the world. We do some basic processing so that they're ready to do the science they want to do with the data. And then once they have the data, for doing the data analysis. So once you have an observation, looking at what you're looking at, whether it's a star, a galaxy, a gas cloud in the universe, how do you actually translate that into some type of real understanding about the universe? Obviously it's very important to actually then take all these things for how we monitor the performance of the telescope, for how we reduce the data, for what the science is coming out, for reporting the results. And then a very key and a very important thing is also finally teaching and using our results in the development of what we're doing to actually educate the next generation of astronomers. This is very important, especially in South Africa. And so the project that we're actually using this with, and Python is the glue that is binding this all together, but what we're using it for is for the Southern African Telescope. And this is located, SALT is located in Sutherland, which is about 4.5 hours northeast of Cape Town. And it's a very vast and remote area, which is great because it makes a very dark sky. But here's the plateau where the telescopes are located at. And this is the Southern African Astronomical Observatory site in Sutherland. The small telescopes are in the background, but the main optical facility is the Southern African Large Telescope. It's a 10-meter diameter telescope, and here it is in the front. If we take a closer look at SALT, what you can actually see here, the primary mirror is 11 meters in diameter. It's the largest telescope in the southern hemisphere. It is 91 1-meter segments created in a spherical shape and basically acts as a giant light bucket. The idea is to collect as many photons as you can get from an astronomical source. These photons are then actually focused, so the primary mirror is actually set at a fixed angle, which is ideal for observing things like the Large Magellanic Cloud. This is a small galaxy which orbits around our own galaxy, and it was one of the most nearest by galaxies. And the orientation of SALT has been actually fixed to actually optimize for observations of this object, but it is also able to observe a wide range of other objects all across from near-Earth objects at the edge of the universe. But the primary mirror takes the light observed by an object and focuses it at the tracker, and the tracker acts to follow stars across the night sky. And all of our instruments are located at the tracker, and that's where actually, as I said, the light is focused, and it does all the hard work. I don't know if we can dim the lights at all in here. But to kind of give you a perspective of what it's kind of like at a night at SALT, I have a short video here where this is, and hopefully you can see it, but this is actually from the perspective of the tracker. And unfortunately, maybe I'll turn this away as well. Whoops, let me restart that. Unfortunately, I'm not sure if the contrast on the projector is good enough to see it, but and maybe for some closer you can actually see it here, and I'll happy to show it to anyone else afterwards. But the tracker actually follows objects around the star, and the telescope moves around throughout the night making observations. And throughout the night, the telescope is Q-based. It could be making observations for a number of astronomers all around the world. It could be observing anything from near-Earth asteroids to, as I said, objects at the edge of the universe. It moves to point to what's called the CCAS tower to help align the primary mirror so that it's actually producing the best image quality. And throughout the night, it will make a wide range of different observations, allowing us to do a wide range of different science projects. Here it's actually targeting a supernova in a nearby galaxy. And here it looks like actually, well, that last one was doing a comet. Obviously, this is a time lapse, so it's sped up a little bit. But this is basically what it looks like if you were on the primary mirror observing with SALT throughout the night. So it's a nice little video put together by one of the astronomers who used to work at SAO, Bruno Letarte, who's now working at Northwest University. And here at the end of the night at the Sutherland Plateau, obviously, and here's the credits for Bruno. But what do we actually do? How do we actually take the measurements? And there's two ways to actually do astronomical observations in the optical. One of them is imaging. And so the main primary imaging instrument is SaltyCam. And what we can actually do is, basically this is just taking a photo. Typically it's taken in small, narrow bands. And let me see if I can get this to restart. But if you can actually follow the little object which is moving along here, that's actually a near-Earth asteroid. This group of scientists from Poland are actually using SALT to observe near-Earth asteroids and measure how they're rotating. So they're actually looking for asteroids that will one day be actually good asteroids to actually land a science or a space mission on. Obviously, you want a slow rotating asteroid because it'll be a lot easier than a fast rotating one. The other main way, and this is really how SALT produces most of its science, is through spectroscopy. Now, everyone here has seen an example of spectroscopy. We've all probably seen a rainbow or a prism that breaks up light into its individual different components. And that's basically what the spectrographs on SALT do. They break up the light into individual components so we can see from exactly what wavelength each photon of light is coming from. And in this case, we can take a look. This top spectra here is a spectra of a star. And what we can actually do is from each of these wiggles, which are in the star, are actually due to different elements. So we can actually fingerprint the star and actually measure what the star is made of. Here we're looking at what the calcium and the iron content of that star is. The other way to actually use spectroscopy is to actually measure motions. By looking at the shift of these spectral lines, we can actually measure how fast an object is moving. And here's an example of a SALT spectra of hydrogen gas in the spectra. And what's happening is that as the galaxy rotates, some of the gas, here's an example of the galaxy, here's an example of the spectra. As the galaxy rotates, as this part of the galaxy moves towards us and that part of the galaxy moves away from us, the spectra and certain spectral lines actually get shifted in different directions. And we can actually then measure how fast that galaxy is rotating and hence derive basically how massive that galaxy is. And so in order to do these, do spectroscopy, we have two main instruments on SALT, which is the Robert Stobie spectrograph, named after a former director of SAO. And I actually much prefer this image of the RSS spectrograph because it slices and dices light in all the different ways possible. And it's a very powerful spectrograph and our very workhorse spectrograph, and a great way to actually do and analyze data from objects in a wide variety of ways. Our other main spectrograph is the high-resolution spectrograph. And this spectrograph is very, very cool because it has basically very high resolution and very high stability. So basically, we can measure how fast a star is moving down to about 1 meter a second, which corresponds to about the speed you walk at. So we can actually measure stars around other systems or other stars outside of the sun to actually look for small wobbles, which might be caused by planets which are orbiting around them. We can also use the HRS, for example, in this recent result, to actually study objects which are actually exploding. This is a case of a star undergoing a small nova explosion. And so basically looking at thermonuclear explosion on the surface of a star, which is kind of cool. We can actually use the high precision of HRS to actually measure how strong winds are coming off of the star and the surface of the star. And so how do we use Python to actually get some of these wide range of different science results? And one way is actually on Sky and in real time. And so we actually build a number of GUIs for the, or graphical user interfaces for the SALT astronomer, the person who is at the telescope doing the observations, to be able to look at the data. And these are actually based off of PyQt4. And these, what they allow them to do, take a quick look at the data, determine whether or not the data is useful or not useful, and also it will quickly distribute the data to the principal investigators if the data is of good quality. They can actually then go and quickly do their science. Some examples of very quick follow-up science done by SALT are supernova observations. In this case, Dan Milosevich, who works in Dartmouth University, used SALT to actually study supernovas. What he did was monitor, basically would look for, basically every day in the afternoon, Dan would email the telescope and say, there's this interesting supernova that just went off in this galaxy somewhere else. He'd email them about 5 p.m. They'd get the submission of his proposal by about, maybe the object is up then and visible at 7 p.m. They get the telescope, they point it at the object, they get the spectra, they send it, process it, send it back to Dan, who would then actually analyze the spectra and then post his results and say, this is a really cool supernova, get more data. And so in this case, he actually monitored the supernova for over about 300 days to actually see how it was evolving and to see actually what is made up of the supernova, how the explosion evolves over time. And basically, we can then actually better understand what type of objects these supernovae are actually from and use them to actually help explore our universe. But it's only having these really easy, accessible tools to actually quickly distribute the data using basically mainly basic standard Python packages for emailing, keeping track of the data, and distributing the data, and also for building interfaces for the astronomers to look at the data. As I said, the main heart for our observatory for handling the data is our data pipeline. This is now what we actually use to actually reduce the data and to actually take a look at the data. And the pipeline basically runs every day at 10:30 a.m. So after a full night of observations are taken, the pipeline runs and basically processes through the data and then distributes the data to our wide range of investigators who are basically all around the world. We have New Zealand, India, Europe, the US, and also a lot of investigators in South Africa, of course. Basically, the pipeline goes through a number of different steps, including preparing the data, cleaning the images, removing all these systematic errors which are in the images, creating the documentation, measuring things about the data quality, recording the data and the information about the data in our MySQL database, and then archiving the data and providing the data online to actually for people to actually download, and then alerting the investigators to the actual availability of their data. And other than basically cleaning the images, most of the other stuff is built by standard Python libraries plus interfaces with the MySQL database. And as I said, one of the things this allows us to do is to monitor the performance of the telescope. This is an example of our monitoring the weather performance and a beautiful interface built by Paul Kotze using basically matplotlib to actually monitor various weather parameters about the telescope, to look at the wind speed, the seeing, the humidity, and actually see how the telescope is actually performing at any given time. We also use a wide range of different things to actually look at things such as measuring the performance, how often is the telescope observing, how much is it down for downtime, monitoring the quality of the telescope. Are we losing throughput due to an increase of dust? Does the telescope need to be cleaned over time? We can actually monitor a wide range of different things and keep track of them. And we've been actually using static web pages and static graphs which are produced from these, but we are now starting to look at migrating to Flask to actually produce more dynamic web pages and to actually provide a greater amount of information for our users. But as I said, the main heart of the pipeline is the data reduction, and everything is done via the PySalt package. And the PySalt package is basically based off of Python and PyRAF. PyRAF is built by basically the Space Telescope Institute, which runs the Hubble Space Telescope, but it basically is a Python wrapper for a legacy astronomy code called IRAF. But the PyRef wrapper gives you basically all the, basically gives you a more Python interface to the data. But including that, we've also built around NumPy, SciPy, Matplotlib, and also the AstroPy package, which is I'll mention a little bit later as well. And it basically is built on, but basically gives you a number of different tools for actually analyzing the data, reducing the data, and analyzing the data. So we have, these are all now built at SAO in-house and built on primarily Python to provide tools for doing basic CCD reductions, with CCD as our imaging camera, tools to actually convert our spectroscopic data reductions into wavelength calibrated reductions, tools for actually analyzing some of our different modes, like our high resolution spectroscopy, and also tools for actually doing analysis of, we also have a very unique mode of high-speed photometry on the telescope, which I'll go into a little bit more detail. But some of these have actually led to further developments into different packages, for example, the reduction of science-grade data, which is the CCD proc data. Astronomers use charge-coupled devices, which is the same technology in your phone, but just the camera's worth about $500,000. And so, and they're cooled to about minus 160 degrees. And so, these are, we really want to clean up every last little speck in these data to actually make sure we're getting every last photon that we can observe. Because sometimes we're only getting a handful of photons to actually look at our objects. And so we have developed pure Python packages for actually reducing and analyzing these data. In addition, we've developed different tools, once again, built on PyQt4 to actually do wavelength calibration. And the nice thing is that the astronomy community has been growing more and more to actually develop and adopt Python. One of the things I set up for reducing this is a package to actually model spectrographs. And now others are actually going on to adopt this model to actually use at their observatories. And so there is actually a very large community of astronomers using Python and sharing a lot of code, which is actually very helpful. And once you actually reduce the data, we can do actually certain different types of analysis and data, different types of science. And this is an example of using the Robert Sobe spectrograph to actually do some analysis on galaxies which are at very high redshift. And so this is actually combining, this is Liatole Lu at UNISA, who is combining data basically using lower redshift galaxies, which are actually causing higher redshift galaxies to be magnified. And so he's using galaxies which are relatively nearby to us. They're only about 3 or 4 billion light years away. But he's using those to actually study galaxies which are 12 billion light years away. And he's able to actually use the reduction pipeline to actually analyze a large number of data to find these galaxies which are actually really doing the lensing, and to confirm their presence and to help build up the geometry to actually study these very, very high redshift galaxies. Likewise, the tools for SALT also produce tools to analyze data. And so this is an example of once the data is actually reduced, we want to do the photometry and to determine how much light is coming from a source. And this is, as I mentioned, the imaging camera actually has a high-speed mode, where it actually takes can take frames at basically a rate of about 10 hertz, or about 1 frame every 10th of a second, to actually study astronomical objects. And so even stars change, certain stars actually change on these timescales. One example of using this is by Steve Potter and Encarni Romero Combinero at SAO. And here you can see an example of this. If you watch the star over here, you should actually be able to see it get fainter and then get brighter. And what you're actually watching is another star which is actually being eclipsed by another star which is orbiting around it. And what we're actually doing, hopefully maybe I should put that on repeat, but you can actually watching another star which is being eclipsed and what we're doing is actually measuring exactly when those eclipses happen. And what they did, they measured these eclipses, and the data from SALT are actually at the top and highlighted in red there. To actually measure these eclipses where they happen, they noticed that they drifted. And the likely cause is that you have these two stars which are orbiting around each other, but then you also have planets which are orbiting around those stars, and they're causing a drift in the orbit of the two planets. And so they actually were discovering a system which is like Tatooine, where you actually have two stars in the sky, which is, I don't know, I find that cool.
So it's the opposite.
I know.
Yeah, I want to see the opposite impression of it.
Yeah, I know. Yeah, I did have a Star Wars picture in here, but I think I took it out. So, and so, as I mentioned, there's a large community of astronomers who are using PyCon. And right now, one of the biggest activities right now is the AstroPy package, which is actually basically built off of Python, and then you have the NumPy libraries, the SciPy libraries, and the scikit libraries. And AstroPy is using and leveraging those libraries to actually develop tools for astronomers for Python. Right now, there's over 80 different astronomers who have been contributing to the package, including at observatories at SAO, at the Hubble Space Telescope, at Gemini Observatory, and at basically institutes all around the world who are actually contributing to this package to help make it better and to actually make things useful. Basically, so we're also not all redoing the same thing. Some of the packages are actually basic packages for things doing like coordinate systems in astronomy. Some of them are then actually more advanced for doing different cosmologies, so we can actually, when we're actually checking our results and doing our science and looking at exactly how far away a star is, we can actually have a built-in package. Some of them are for doing I/O. Most astronomy data comes in a format which is called FITS. And so the package for reading and writing in that data it has been converted to a Python package in AstroPy. The advantage of this is that we then have the base AstroPy package, which is then developing into a whole core of different packages. And here on the right is the affiliated packages of AstroPy. And you can see, for example, CCD-proc package. But there's also packages for graphing astronomical data, like ApplePy. There's also machine learning packages, AstroML. And a wide range of different packages which are now growing out of this AstroPy activity, and coordinated effort between a large number of different astronomers to actually provide an open source and usable library for doing astronomy with Python. And so, and obviously to get to my last part here is it's very critical and important. And I think if you attended Lars' talk, you also saw a lot of examples of using Python for teaching with astronomy. And I also teach as part of the National Astrophysics and Space Science Program, which is a program to actually give students who are coming, especially from previous disadvantaged universities and from all over Africa, a chance. It's an honors level course and an introduction to astronomy. So they can actually get caught up on everything they need to know about astronomy and then go on to do their master's and their PhD. Typically, we have about 20 students per year, but the base language for the course is Python. So all of their courses are taught in Python. In addition to teaching at the NAS course, we also have a number of online tutorials and also a number of workshops, which we also use to actually introduce Python to the community, to actually use it to expand the number of things that we're doing, and it is actually a great resource. I don't need to go into too much detail about this because Laura did a fantastic, Toby, who gave previous talks on IPython notebooks, but it is an incredible resource, especially for teaching and for keeping track of what you're doing. And we've been setting this up for our CCD-proc tutorial with Matthew Craig in Minnesota. And then it's also a great tool for collaborating, for actually sharing data and what you're actually doing. One thing I've actually recently done for my tutorial is I've actually had online questionnaires. And I've been using actually Sculpt, which actually allows you, or an easy JavaScript interface for actually embedding Python code into your websites. So it's a nice combination of actually allowing to actually put code in so the student can type it in and then they can actually have a button for checking their work. And so it's, then you can actually publish what the result is so they can actually either graph it up or take a look at actually what they're doing. And so, and it was actually quite easy to actually integrate something. There's Sculpt, and then there's also Trinket, which is a wrapper on top of Sculpt for actually doing this type of stuff. But I think that actually sums up what I was hoping to tell you about today. And that, fortunate enough, due to Python's extensive library, ease of development, support, and diversity of applications for it, it's made it actually really incredibly useful for to be able to quickly and productively do science, and makes it actually very easy to share it as well. And so there obviously is a lot of people here who actually I do want to thank. I'll specifically say Gareth because he's actually in the audience, and I'll make him wave. Gareth, and but the huge team at the SALT astronomy operations, along with a number of other people, and the huge AstroPy collaboration, along with support from South Africa and the National Research Foundation, which has made a lot of my work possible. And so, and then I'll just end up with the references if anyone is actually interested in some links to some further information and looking at stuff. But thank you very much for your time.
Thanks, Steve. We've got 15 minutes, so hopefully there's a few questions.
Could I ask one? You mentioned MySQL possibly switching to Flask. That's the back end to the web
Interface,
distribution of information. What do you use for long-term storage? I mean, it's a lot of data. Is it MySQL as well, or is it another data store?
For the information about the data, we use a MySQL database, and for the actual data itself, we generate anywhere from 10 to 50 gigabytes a night. So
it's tough to put in a database.
Yeah. So it's not, the data itself is not directly in a database. It's just in a Unix file storage system.
Can I ask you a question about that? I mean, you know, it sounds like you use Python for everything that you can use it for, because it's easy to write stuff in Python for just about everything. So all these, you know, stuff that you got to do every day, like store all the data, the 50 gigabytes you got. Do you use Python like as a sysadmin, netadmin, and all that, just the whole 9 yards?
I'd like to move towards that. It's mostly bash and mostly.
Okay. So,
Pretty short answer for you, but it is.
but for the front end web
But,
part
yeah.
that distributes the information, it's definitely a Python deal.
Yeah.
So
So
thanks.
we're trying to move probably as much as we can to Python. I mean, most of the front end stuff is currently moved over, but we're definitely moving over. We do have a number of different cron jobs that run every day, which are all Python based, and a number of other things. And so use it as much throughout our system as we can.
Hey, thanks a lot.
Actually, that's related to a question I have. You said it was 50 gigabytes a night a telescope produces. So if you want to disseminate that data to people overseas, how does that work?
Yeah, I should preface it. Our average is 10 gigabytes a night.
Okay.
And so when certain instruments are running, then we can hit kind of the 50 gigabyte. And although in the next 3 to 4 years, we actually expect that to actually grow to up to 250 gigabytes a night. And you know, right now, we primarily just compress all the data, put it into a tarball, and zip the data, and then put it on a website.
And they download it.
And they download it. And basically, using wget seems to actually work
That's
nowadays.
That's why my Netflix is so slow.
Yeah. Fortunately enough, we're on the research infrastructure, and then so it gives us actually a pretty quick link to the CCAP. Yeah.
Yeah, so I work at SKA, and
Yeah.
it's, of course, it's a huge problem for us because we're generating terabytes a night.
Yeah,
And
no,
we
it's a
can't
different scale.
disseminate.
SKA is a different scale of problem. Yeah.
You obviously don't just store all the data and then analyze it. Do you analyze it as it comes past?
Yeah, so basically the one thing we have at the telescope is some tools actually analyze it in real time. So that basically you won't be able to do the final analysis because you need a number of calibration frames and other things to actually fully do it. But a lot of it you can actually do you can get about 80% of the way in real time. And so that's why we do have that set up at the telescope. So there is an option for the observer or for the investigators where they can actually select they'd like their data in real time. And they're basically emailed a final or a preliminary spectra, basically as it comes off the telescope. It's from it coming off the telescope to them getting it is under a minute.
I'm
So-
sorry, can I just jump in on that question? Was that PyQt GUI slide you showed? with
Yeah.
the Spectrum?
Yeah,
Okay.
so that's so the GUI and the interface is built on PyQt 4, and then but the backend for doing this is actually all in
Sure,
Python.
but that was the tool you were just talking about.
Yeah, so that's the tool that we developed to do that. So.
You mentioned you use IPython a lot for tutoring and stuff and collaboration. Is that, are you using multiple IPython instances together, or are you enabling the network mode? Do you ship the notebook file itself to someone else when you finish work on it? How do you actually go about doing that?
I probably use it more in that mode. I have to admit, I have not fully explored the full networking mode capabilities of it. It's been more of the, once you've actually done something,
Package
package it up and send it over, and so that you're exchanging notebooks. Yeah.
Do you guys have any kind of like almost manholes into any of your other systems where a notebook will integrate into another remote service and be like a real-time
I think that
inspection system?
it's been kind of, if not a notebook, but something that was similar to that, is something that we've often talked about, wanting to have, and things like SKA will actually certainly need things where they're not going to be able, that you don't ship the data, but you ship the working on it. And we had previously investigated someone with looking at cloud usage as well, and it's just something that we haven't had enough time to fully investigate. So, but something kind of always been a, given more time, we'd love to look at it. So.
I'm sorry, I don't want to be a question pig, but can I be?
Go next.
You mentioned really tight tolerances, like you can detect this huge star moving at a meter, whatever. Obviously, that's a lot of floating point precision. You got several layers of software in there, from the raw electrical engineering stuff for the $500,000 camera and its processor, all the way up through the scientific Python and the Python that you use to reduce the data. Is all that stuff dealt with? Is that what you pay the $500,000 and super cool for, or do you actually do some of that phenomenal precision work along the way?
Yeah, so for that phenomenal precision work, what they actually have to do is they actually send the light through a glass tube containing iodine gas, and then actually take an image of it. And basically, the iodine gas imprints on the spectra, basically very precisely where that spectra is actually located at. And then you actually have to do the analysis. So you get the data, but then that doesn't just give you what the result is. You do then have to do the analysis on it to actually very precisely predict, exactly where the lines are falling, and to, and this is some stuff that we actually still need to work on. For example, it's like how well you can centroid the lines. So, for some of these very high-end needs, you're trying to centroid the line to about 1,000th of a pixel. And so, that's actually where, how good your software is becomes very, very important.
So it's not just you pay for this phenomenal piece of equipment, you pay for the phenomenal piece of equipment, and then you have to keep working at using it better and better with your C and Python skills, and using the packages.
Arguably, you'll end up paying, you won't end up, unfortunately, instruments aren't always budgeted with software in mind and how much they actually really need to be successful. But the budget for actually what is actually required is actually quite high. And so
It's
you
a
can
lot.
have a team of astronomers who are actually, if you have 10 astronomers, you can think about how much each of those cost to actually produce very high quality scientific results.
Astronomers are
I know.
expensive.
It's a lot of people working very hard. So
Yeah,
good.
yeah.
Yeah, there's one
Thanks.
well-asked question.
You're a really popular guy.
I am.
Everybody your time. It's actually related, but I've got 3 questions.
You've got 7 minutes.
I'll get to 5 questions. Your picture of spectrograph earlier on, where you had calcium and
Yeah.
ferrous metal. With that, the question really is, how good is your accuracy? You've got the qualitative side and the quantitative side. So you've got you
Okay.
can tell what's in it,
Yeah.
but can you tell how much and how accurate is it?
Yeah, so the black, sorry, I didn't actually fully explain this. The black line here is the observations. The red is the model. That's our theoretical prediction
Okay.
for what the spectrum should actually look like.
Standard versus convective,
Yeah, so you can see it's not obviously perfect, but probably our models, our stellar atmosphere models are probably getting very, very accurate.
What's the emission on that?
I think that actually might be H alpha. So
In the star?
yeah, around the star. It's a young star, so it actually might be. I think that might be right around H alpha. So yeah, I know. We'll get too deep. So, it depends a lot on obviously how much the precision of the spectrograph. This is coming from RSS, which has basically a resolution of what astronomers say is a resolution of about 10,000, which corresponds to about roughly about a half an angstrom. So how accurately you can basically, or your resolution element, how accurately you can resolve one of those lines is about half an angstrom.
Okay.
And so, which is 0.05 nanometers, and so, yeah, so very, 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 very small. The other spectrograph can go, that has modes up to about 70,000, a resolution of 70,000, so you can divide that half an angstrom by another factor of 7. And so, but it depends on how much signal noise you have, what your techniques for analysis are, how good your models are, and so there is a lot of stuff that comes into it. I would say a good thumbsuck of like how well we can know how much metals are in a given star would be, I mean, for a star, I'd probably say to a few percent. For something like a galaxy, I'd say 10%. Because you have a lot of other stars in it, and so they blend together. So you're limited by the systematic, or you're limited by the intrinsic nature of the object sometimes. So.
The other thought I had was whether you guys were using neural networks for pattern recognition at all?
Not right now for this stuff. I've used some of this. I've used neural networks before for some other code that I've done back in a previous life when I coded in C. Yeah, I know. I still have flashbacks. But yeah, so there is one of the astronomers who's very much involved with machine learning and Python, or one of the persons very much with machine learning and Python, like the scikit-learn package, is an astronomer, and they do a lot of stuff like that.
So there's some research going on.
Oh yeah, and they love our data sets because they're a lot of them are
There's a
few.
lot of data,
There's a lot of data and they're free often.
Great. Okay, third question. Found ET yet?
Not yet.
You use
Not
that
yet.
saying,
I
but
know.
not
We'll find the planets. They'll follow up for the Britney Spears radio.
That's it, yeah. We'll find out what they're listening to.
Yeah, exactly.
Hi there, I have a question. How do you queue the work? Do you have like a web interface where guys log in and to it, and then they have like a tie-break algorithm, or?
Yeah, so that's actually one bit of code that I didn't actually talk about is our queue schedule algorithm, which is actually it's still in development, but that does actually goes through and you can basically at the beginning of the semester people fill in what they want to observe, and sometimes you get things that do come in on a given day, which are target of opportunity observations. But basically what happens though is that there is a queue that is then set up for what should get observed. Conditions change, weather changes, so that queue can get mixed up. But basically, each possible observation gets a score, and then the algorithm would go through and actually figure out, using like simulated annealing techniques or a greedy search, to actually look for what would be actually the best observations.
Does the observer then choose
And then
top of the list, or do they sometimes, is there human intervention?
Yeah. So right now we still have a human intervention where the observer, the salt astronomer who is on duty and doing the observations, then says, okay, yes, that does look like the best one for us.
Because I would use Bitcoin as my tie-breaking algorithm. And also, it would be cool, like, do you guys do like a lot of asteroid hunting, mining for that? Because obviously that's very interesting, especially for near-Earth objects.
Yeah, we have, for SALT, yeah, well, I unplug so you can. For SALT, we have a narrow field of view, so we don't necessarily, we image a very small area on the sky, so we don't necessarily have a good possibility of finding asteroids. But there's other surveys, some done from Sutherland, which have a very wide field of view, and they're great for picking them up. Well, what they'll do is they'll find them, and then we'll follow them up. So,
Cool. Thanks very much.
thank you.
Filing it as well, I forgot to mention